Hello, everyone. Welcome back for Module 1, Part 2 in the Fundamentals of Light and Laser class. So as we start speaking about the particle properties of light, I'm going to start off with equation 111 in our textbook. And that equation is E is equal to h nu, where E is the energy of the photon in joules, nu is the frequency in hertz, and h is Planck's constant, which is equal to 6.625 times 10 to the negative 34th joule seconds. Then alternately, because we know that nu is equal to c over the wavelength lambda, the energy can also be expressed in terms of the wavelength lambda and the speed c of light, and equation 112, which is E is equal to hc over lambda. And again, that's energy in photon of the photon in joules. C is the speed of light in a vacuum. H is Planck's constant, and lambda is the wavelength in light, wavelength of light in meters. So just as a little example, to calculate the energy of a photon of a given frequency, so given that the frequency of a photon of a helium neon laser light is 4.74 times 10 to the 14th hertz, to find the energy would be E is equal to h times nu. H is given as 6.625 times 10 to the minus 34th joule seconds. And we were told that the frequency of the photon of the helium neon laser is 4.74 times 10 to the 14th hertz. So if I multiply those two, I get that my energy is equal to 3.14 times 10 to the minus 19th joules. So I could also find the energy of a photon by its wavelength. So in example 7, we're given that the wavelength of the helium neon laser is 633 nanometers. So we have to find the energy. So I'm going to use the equation that my energy is equal to hc over lambda, which is equation 1-12 in our textbook. So Planck's constant h is 6.625 times 10 to the minus 34th joule seconds. And the speed of light in the vacuum is 3 times 10 to the 8th meters per second. And we're given that the wavelength of the light is 633 nanometers, which is actually 6.33 times 10 to the minus 7th meters. And we see that the energy is 3.14 times 10 to the minus 19th joules, which is actually the same as it was in the previous example. And that makes sense because of the fact that it's the same helium neon laser. In one case, we're given the frequency, and the other we're given the wavelength. So reflection from plane surfaces. When a ray of light is incident on a plane, reflecting surface such as a mirror or window pane, all or some of the light is reflected. The part that is reflected obeys the law of reflection illustrated below. This is figure 111 from our textbook. So if you look at that, we have an incident ray, and then we have a reflected ray. We have an angle A and an angle B. And it says here, incident ray, reflected ray, and normal all lie in the same plane, which is called the plane of incidence. So refraction at an optical interface, when light is incident on an interface between two transparent optical mediums, distinguished from each other by different indexes of refraction, N1 and N2, as shown in figure 112, part of the light is reflected and part is refracted. The reflected part obeys the laws of reflection. The refracted part obeys Snell's law. So here is that figure, and you see I have medium 1 and medium 2, and I have incident light, and you see part of that light is reflected back, and then we have theta 1 and theta 2 there. And I'm sorry, theta 1 and theta 1 are both on the reflected side, so they're equal. And then in medium 2, we have theta 2. So Snell's law is written as N1 sine theta 1 is equal to N2 sine theta 2, where N1 is the index of refraction of medium 1, and N2 is the index of refraction of medium 2. And theta 1 is the angle of incidence and of reflection, and theta 2 is the angle of refraction. There is again a link here to an optic video. I suggest that you guys look at these videos because they are very helpful and very informative. This table here has the indexes of refraction for various materials at 589 nanometers. So for air, it's 1.0003. And then as we go down this list, we see like diamond is 2.42. Gallium arsenide is 3.4, glass is 1.52, and that's crown glass. Zircon is 1.92, flint glass is 1.66, and as we kind of move on, water is 1.33 and ice is 1.31. So that's the table that we're going to use. Again, once the lab kits arrive, I will be posting labs for you guys, and refraction is going to be part of one of the labs. So I have another example here, and I'll read it. Basically, I have light incident on a glass slide. A laser beam, 589 nanometers, is directed onto a microscope glass slide of index of refraction on 1.52. The angle of incidence onto the glass is 60 degrees. Question A asks, what is the angle of reflection? And B asks, what is the angle of refraction? So from the law of reflection, the reflected beam heads off at the same angle as the angle of incidence. So since we know that the angle of incidence is 60 degrees, the angle of reflection is also 60 degrees. Now, from Snell's law, we know that N1 sine theta 1 is equal to N2 sine theta 2, where N1 is 1.00, theta 1 is 60 degrees, and N2 is given as 1.52. So if you just put those numbers into the equation, we have 1.00 times sine 60 degrees is equal to 1.52 times the sine of theta. We could rewrite that and say the sine of theta 2 is equal to 1 times 0.87 divided by 1.52, which is equal to 0.572. So then we do the arc sine of 0.572, and we get that theta 2 is equal to 34.9. So the refracted ray must bend toward the normal to the interface as it enters the glass. Now, some of you may be asking why N1 is being 1.00, whereas in the previous table, it said that N for air was 1.0003. For all intents and purposes in this class, because of significant digits and the like, we could just use the 1.00. We don't have to use the 1.003. So the wave nature of light was given great support by Christian Huygens and Thomas Young around the turn of the 18th century. They showed that in phase light waves of the same wavelength coming from two different sources and directed onto a screen could be made to overlap and interfere with each other. Along the screen located somewhat distant from the two sources, the overlapping light waves would reinforce one another and produce regions of higher light intensities at some point, At other points in between the bright spots, the light waves would subtract from each other and produce regions of lower light intensities. The series of adjacent bright and dark regions was called interference fringes. Their existence could be explained successfully by treating light from the two sources as waves. So this is a drawing showing that double slit experiment, and what you see here is that we have like the fringes where you have like the bright spots, dark spots, and everything in between. So basically the light waves emanating from slits S1 and S2 are in phase and of the same wavelength. The light waves move outwardly from S1 and S2, overlap and reinforce each other along lines with solid dots. They cancel each other along the lines with the unfilled dots. On the screen, alternate regions of bright and dark make up the interference fringes as shown roughly in the offset. The dark regions shown are darkest at their centers and fade out gradually into the white regions. Similar fading occurs as the white regions blend into the dark regions. When light passes through small openings or by sharp boundaries, such as a razor blade edge, interference of the light wave produces diffraction patterns. These diffraction patterns exhibit fringes and extend into the regions of geometrical shadow where light treated as a beam of particles could not go. So this figure shows different, it says beautiful diffracting patterns obtained when light is passed through a circular pinhole, which is 1.14A, through a narrow slit, 1.14B, and a sharp edge, 1.14C. Absorption and scattering of light. When a light beam passes through an optical medium, some of the light is reflected at the two interfaces, some is absorbed inside the medium, and some is scattered outside of the beam. While in the medium, and what is left is transmitted. This is shown schematically in the sketch in figure 1.15. In this figure, the width of the light beam depicts the energy contained within it. As the beam passes through a medium, its physical width stays constant, but as illustrated in the figure, its energy content decreases as photons leave it through reflection, absorption, and scattering interactions. So here I have a figure of the atomic model, and it's actually showing here that electron is getting excited from that state E1 up to E2. And we said it last lecture, and I'm going to just repeat it here, that light is emitted when that electron drops from a higher level to a lower level. So in this case, when going from E2 to E1, this is emitting a blue photon, and when going from E1 to E0, it is emitting a red photon. So here is an energy level diagram for a hydrogen atom, and we could see the different levels of N and then as it drops, you see the energy level that's emitted there. So everything from N equals 6 going down to N equals 1, and you can see how when the photons drop, they have different energy levels. So suppose a hydrogen atom is in an excited state, say the N equals 3 level. The atom can make a transition to the ground state by emitting a photon. The energy of the emitted photon equals the decrease in energy of the atom as shown below. So my energy of the photon is E3 minus E1. So in this case, it's minus 1.51 electron volts minus 13.6 electron volts, which is 12.0 electron volts. The atom can also absorb photons. This happens when the energy of a photon exactly matches the difference between two electron energy levels. For example, a hydrogen atom in the ground state can absorb a photon whose energy is 12.09 electron volts. The electron in the atom will then move from energy level E1 to energy level E3. So we're going to talk about the spectra of light sources now. And basically, that figure 118 shows the typical emission spectrum of a monatomic gas, such as helium or neon. This type of spectron is produced by an electrical discharge passed through a gas sample contained at low pressure. Each of these lines in the emission spectrum is produced by a single atomic transition from one energy level to the other, and the intensity of each line produced is dependent on the probability of atoms making that particular transition. Stronger lines are the result of more probable transitions from energy states having short atomic lifetimes. Weaker lines are the result of less probable transitions from states that have longer atomic lifelines. And as you notice, I have the higher that peak is, the higher the intensity is. And then as I am moving to the right on this graph, my wavelength is getting bigger. So absorption spectra is a little different. It's the transfer of energy from an electromagnetic wave to the atoms or molecules in the material. Energy transferred to an atom, for example, excites electrons to higher energy states. Thus, absorption depends very much on the energy level structure of particular elements or compounds. The wavelength intensity spectrum of light that passes through the material appears to have certain wavelengths removed. Those are the absorbed light, and this is called the absorption spectrum. Selective absorption explains why different objects that we see have different colors. For example, a red apple is red because the skin of the apple absorbs all colors incident on it except red, which it reflects to us to see as red light. Figure 119 in our textbook represents the typical absorption spectrum for a solid material. Unlike the comparative narrow spikes of a gaseous spectrum seen in the previous figure 118, the spectrum consists of broad, irregularly spiked regions called absorption bands. Areas containing a closely spaced group of strong lines appear as an absorption band in crystalline solids, such as the NdYAG, which stands for neodymium atoms in yttrium aluminum garnet. These absorption bands consist of groups of closely spaced sharp-edged lines in solids such as Nd glass that lack an ordered crystalline structure. The bands are broader and less distinct. The wavelength characteristics of these absorption bands are important in determining the type of electromagnetic radiation we should use to excite solid-state lasers. So here is that figure, and you can see how those peaks going up are different than they were in the previous slide. Black body radiation. The spectrum of electromagnetic radiation emitted by an object at some absolute temperature T, generally referred to as thermal radiation or black body radiation, is shown in figure 1-20. Three thermal radiation or black body radiation curves are shown at absolute temperatures of 1600 degrees Kelvin, 2400 degrees Kelvin, and 3200 degrees Kelvin. Note that as the temperature rises, the amount of light area under the curve increases and the peak radiant power, P, shifts towards shorter wavelength. It was precisely in the challenge of accounting for the detailed shapes of these curves that Max Planck hypothesized the need for quanta of light, photons, and gave birth to the field of quantum physics. The shift in wavelength of the emitted radiation of a thermal source as it is heated is familiar to most of us. We see an object become red hot as the temperature increases. That's because a larger amount of radiation is being emitted in the red part of the spectrum. If we continue to increase the temperature, we move toward the white hot level. I don't know if anyone has ever witnessed this or seen it, but I have, in a kind of a weird way, I've seen metal become red hot when in use. And the time that I saw it actually was actually when I used to race cars. I came off the track one race, and I popped open the hood, and at the time I had a turbocharged car. And when I looked at my turbocharger under my hood, the turbocharger housing was actually glowing red, which tells you how hot that got during that race, right? So that's the one time. And then another time it actually happened where I witnessed a car come off the track, and I could see through the front wheels that the brake discs were glowing red, and the person actually was suffering from severe brake fade because his brakes overheated, and they overheated so much that they were glowing red. So, that does happen, and you can witness that in real life. So here's an example of those curves, and you could see that as the temperature gets higher, the power emitted gets higher also. So here I just want to introduce one other equation, and then we'll go through a quick example. And the equation is 114 in our textbook, and it basically tells us the shift of a peak wavelength as a function of the absolute temperature is given by the so-called Wien displacement law, which says my maximum wavelength times my absolute temperature in degrees is equal to 2.898 times 10 to the minus third meter Kelvin. So in this example, it's assuming a black body, assuming a body is at room temperature of 68 degrees Fahrenheit is actually 20 degrees Celsius, which is 293 degrees Kelvin. What is the peak wavelength of the thermal radiation given off by this body? So if we treat the body as a black body and we use equation 114, we're going to say that we arrange the equation and say that our maximum wavelength is going to be equal to 2.898 times 10 to the minus thirds meters per degree Kelvin, and divide that by the temperature, which is 293 degrees Kelvin, and we get it's 9.89 times 10 to the minus 6 meters, or 9.89 micrometers. And again, it's an example of what happens with the temperature. So the next slide here actually shows the scattering of light. And the scattering of light is redirecting light, and that's caused by it interacting with other matter. So the scattered light is either going to have the same or longer wavelength compared to all other incident radiation, and it actually may have different polarization. So if the dimensions of the scatterer are much smaller than the wavelength of light, like a molecule, for example, the scatterer can absorb the incident light and quickly remit the light in a different direction. If the remitted light has the same wavelength as the incident light, the process is called Rayleigh scattering, and that's what we see on the left-hand side of this figure. If the re-emitted light has a longer wavelength, the molecule is left in an excited state, and the process is called Raman scattering. And in that in Raman scattering, the secondary photons of a longer wavelength are emitted as the molecule returns to the ground state. In general, air molecules, oxygen and nitrogen, are Rayleigh scatterers of visible light and are more effective at scattering shorter wavelengths such as blue and violet. So since they scatter those wavelengths more, that could be part of the reason our sky is blue. If the scatterer is similar in size to or is much larger than the wavelength of light, the existence of a matching energy level is not important. All wavelengths are equally scattered. This process is called Mech scattering. And so an example of that, water droplets effectively scatter all wavelengths of visible light in all directions. So now we'll speak a little bit about laser safety. And this is an important topic, and I think we kind of disregard it, but we cannot. And so the first thing that we must know in laser safety is that do not look directly into the laser beam, right? And it says here like a low power helium neon laser is a little more than a coherent monochromatic light bulb. The common laboratory Heine laser described here is not capable of burning or drilling holes in most materials, and accidental momentary eye exposure will not normally cause eye damage. Nevertheless, the highly directional, intense beam of light should be treated with caution, care, and respect. Common sense dictates that one must not look directly into any bright light source such as the sun, a carbon arc, or an arc lamp projector, and particularly a laser beam. The lens of the eye can focus a beam from even low-powered 1 to 5 megawatt helium neon lasers to a small spot in the retina, on the retina, and cause thermal damage to the retinal tissue. Do not look at specular reflections of the laser beam. So specular reflections are those from mirrors, watch crystals, polished metal surfaces, painted and unpainted, or any other highly reflective surface. Specular reflections of a laser beam are considered secondary laser sources and as such are treated with the same caution as one does the direct laser beam. So a word of caution, and one of the things that I do personally, even with low-powered lasers, is when I'm doing a lab, I will not wear jewelry such as my watch or a ring or anything like that, because I don't want that reflection going somewhere where it's not necessary and where someone may look at it. Now, that may sound a little like overkill when we're dealing with lower powered lasers, but I want to instill in everyone in this class that the safety precautions, while they are important across the board, I want to make sure that they become almost automatic for everyone here, so that even when you're working with a lower powered laser, you're taking appropriate precautions. So take care when moving the laser or when moving objects in the beam path of the laser. Most low-powered helium neon lasers are small enough to be moved about easily. If the laser must be moved during its operation, care must be taken to direct the beam carefully in order that it will not shine into anyone's eyes. For the reasons outlined above, caution also must be taken not to direct the beam upon a specular reflector when the laser is moved. If an object must be moved into the beam of a laser, the movement should be deliberate, with due consideration given to where the reflections will be directed. And usually a laser should be turned off before it is moved. Beware of high voltage, especially when the case or enclosure of an operating laser is open. again, we'll go back to that helium neon laser, but that we are using here a lot. Even though it's not a high-powered laser, it does contain a high-voltage power supply. It says they should not be disassembled, demonstrated, or serviced by anyone unfamiliar with such devices. Most lasers contain either high voltage or high current power supplies that should be treated with caution. Each year, more people in the laser industry are injured by electrical hazards than by exposure to laser beams. Now, it does say this, they should not be disassembled, demonstrated, or serviced by anyone unfamiliar with such devices. But the helium neon laser that I use in the music demonstration and that I use in labs when we're on campus, I do have to actually make adjustments to it, and I do have to take it apart to do that, but I do have to take care to make sure that I do not touch any of the high voltage or high power, high current areas while I'm making those adjustments, because again, you could hurt yourself with the electricity that's there as opposed to the laser actual beam. So this is going to be a tough one for us because right now we're not at a lab. We're going to be doing our labs from home. But it says operate the laser in an area designed for laser operation. So if possible, the laser should be operated with a beam horizontal and below eye level to prevent eye damage. All potential specular reflectors should be removed from the beam area. Adequate provision for all support equipment shall be made prior to the operation of the laser. The number of persons working around the laser should be kept to a minimum, and the area in which the laser is being operated should be illuminated as much as possible. Access to the operation area should be limited and appropriate warning signs exhibited. Most low-power helium neon lasers are designed to operate with 110, 120 volts, single phase, 50 to 60 hertz AC power. Some may operate with 220, 240 volt, single or triple phase. Prior to the operation of any laser, the correct power requirements for the laser should be determined from the laser specification. The power cord attached to the laser should be examined. For most low-power helium neon lasers, the unit is equipped with a power cord consisting of a 3-wire grounded plug. The 3rd wire grounded terminal must not be bypassed. Now, when you guys, if you actually worked in a regular laser lab, you will also see that between the workstations, many times there will be a dark curtain, and that's done so that your laser beams will not go into the other work area. Since you're going to be working at home with these labs during this time, I'm going to ask that you work in an area that does not have a lot of reflective stuff around, and as it said here, to work with the laser beam below your eye level. So if you're working on a desk or a table, stand while you're working there so your eye is above the laser so the reflection doesn't go into your eye. Also, if there are other people at home with you, please make sure that they're not running into the area that you're going and you're working with at the time. Keep them either outside, or if they want to be in there and want to help you with your lab, make sure that you go over the safety precautions with them also. Do not intentionally or inadvertently track vehicles or aircraft with a laser beam. Federal laws prohibit the tracking of vehicles or aircraft with laser beams. Such actions could cause considerable property damage, loss of eyesight, and even the loss of lives. Yeah, it is illegal to do that, so just keep that in mind. Do not leave an operating laser unattended. Always turn the power to it off when it is not being used. When not in use, a laser should be turned off, again, to prevent accidental exposure to the beam by unqualified persons. Again, very, very serious thing for higher powered lasers. May not be as much of a concern with a small laser, but I want you to get into the practice of doing the right safety precautions. Make sure you follow these rules. You see that caution sign? There are various caution signs that would be put up outside of laser labs. Again, we're working out of our house right now. So at this time, I'm not expecting you to put up a laser sign, but please make it that when you're working on your labs, that there are not people coming in there, and when you stop, turn them off. The lasers that are coming with your lab kits are battery powered, so just make sure they're off before you put them away. You may want to do that also because you don't want to go through batteries unnecessarily. That is the end of this presentation. I hope you all enjoyed it, and I will be posting the first exam, which is on Module 1, on Blackboard shortly after this. Please look for that, and please participate in the chat room, the discussion groups, because your grade is being influenced by your actions in both the chat rooms, discussion forums, and also on these exams and your labs. Thank you very much.